present the new improvement that we have regarding SCIA Engineer 18.1. I would like to start with a few things about GoToWebinar. By default, you are muted now, but you can use the question panel to type your question. Myself and my colleagues from the product department, we will be sure that we will answer your question during or maybe after the webinar. Of course, this webinar will be recorded. You can follow that record from tomorrow, I guess. You will find it on our website, www.scia.net, and also you can find it on our YouTube channel. Basically, for this webinar, in fact, today we have 3 main topics, and we would like to explain those 3 main topics for you during this webinar. The first one is about the multi-material design. I will explain to you what has been changed during 18.1 regarding the long-term deflection, the new approach that we use for the calculation of the ribs. Also, we have some nice improvement regarding the calculation of the compression zone for the NEN National Annex. And then I will explain the new improvement regarding the concrete design, but according to the SCIA code. After me, my colleague Iveta, she will come and she will explain the new improvement for the composite design. And also we have really nice improvement for the steel code. We have nice detailed output in this release. I'm sure this will impress you. The last part, it will be with my colleague Yaroslav, and he will explain to us the new bill of material, the relative deformation, and also which kind of reports that we have today after the analysis. And also he has some nice improvement for or nice news to our clients who are using our engineering reports. He will explain all of that to you. And the last part, it will be regarding the IFC4. So basically this is the content, and I can start with the beginning from the concrete topics. On my list, I have main 3 topics to explain: the new approach for the calculation of the CDD, the calculation of the compression zone according to the NEN National Annex, and some nice improvement for the SCIA code for our clients in Switzerland. So let's start with the main topic, the first one. Basically, I guess you still remember in version 17, we already released the new calculation for the CDD. It was nice improvement where the user can calculate the long-term deflection for 1D and 2D elements in one go. Also, we implemented automatic combination for the calculation of the long-term effect. But unfortunately, we had some limitation at that time in version 17. One of the main limitation, it was about the calculation of the stiffness in case you have a ribs modeled inside your slab. And probably some of you already noticed that SCIA giving this kind of error message to tell the user that be careful, the stiffness was calculated based on some linear approximation. So the result somehow was kind of approximate, but this is not in all cases. This is just in case you have a ribs modeled inside your slab. And as we know, the ribs can be used widely for multi-story buildings. So after the version 17, we received some feedbacks from the clients, and they asked from us to somehow extend the solution for the CDD calculation to include the ribs within the CDD calculation. For that reason, we decided in 18.1 to solve this issue, and the new approach that we use today in 18.1 regarding the CDD calculation is very simple. In fact, SCIA will always look to the intersection between the beam and the slab, and somehow in the background, SCIA will generate a kind of equivalent cross-section to handle the issue of the stiffnesses between the 1D and the stiffnesses of the 2D. And if you go today and you click on the CDD command, you will find the property window of the CDD calculation. And in the property window, you will have this tick box, rib. So basically, you have today two scenarios depending on your decision. In case I'm assuming that you already modeled your ribs inside the slab, but inside the property menu, maybe you would like to deactivate this action. What does that mean? In fact, if you deactivate it, then you are asking from SCIA Engineer to ignore the rib action inside the slab, and in that case, SCIA will calculate the stiffness for 1D and the stiffness for 2D separately without any issue. So it will be quite similar to a case where you have modeled the beam as a beam inside the slab without any rib action. But then, and the next scenario, what will happen in case that you activate this tick box? And here we have two cases, in fact, depending on how you will connect your rib inside the slab. So the first case, you will use by default the connection between the beam and the slab. It will be in the center of the slab. And in that case, as long as you activated the rib action, then SCIA in the background will divide this kind of rib or beam to two pieces for the calculation of the stiffness. And then the part which is belong to the slab and the part which is belong to the flange of the rib will be handled as a 2D member. The second case, you modeled your beam under the slab, so you have some kind of eccentricity. And in this case, it will be more simple for SCIA to handle a case like that, and the idea is still the same. We have one part for the 1D element and the second part for the 2D, and then the calculation of the stiffness will be very clear for us. And then the result we are expecting should be very accurate. Maybe someone will ask, what will happen in case that inside my beam, I definitely have some reinforcement, and this reinforcement will be part of the flange. How does SCIA handle this reinforcement? Also here, what SCIA did, in fact, we will make a summation of the reinforcement coming in from the flange, which is belong to the beam, to the reinforcement which is already exist inside the slab. And in that case, we are not exaggerating in the stiffness of the 2D member. And in my point of view, this is accurate result in that case. So this is basically the idea how we handled the equivalent cross-section for the calculation of the stiffness when you have a ribs inside your slab system. Again, I'm trying to repeat, if you modeled your beam as a beam within the slab, then there is nothing new. It's already implemented since version 17. What I'm trying to explain, this is only valid for a ribs, a slab system. So let me show you that inside SCIA Engineer. And to make the idea clear for you, I'm going to explain that on two cases. The first case, I have very simple model here, like that. I have a T-section to simulate the rib action, and then I have a beam connected with 1 meter slab, and the connection, the amount of reinforcement, everything it's similar. The second case, I have inverted beam, T-beam, something like that, and the same scenario. Here it's 1D element, and here is 2D connected with 1D with some rib action. The third case, I have a kind of X-shape cross-section, but it is 1D. And the same scenario, I connected everything in the middle or in the center. So I would like to test how SCIA will behave in case that I would like to do the CDD calculation. So this is what I tried to explain to you. This is the command of the CDD calculation, and this is the property menu for the CDD calculation. And basically here you can see we have the rib action. As you can see here, I can activate or deactivate the action. So let's try together. I will activate the action. So I'm asking from SCIA to take into account the ribs. First of all, there is no message to telling you be careful, because now we do the calculation automatically. And now we should expect that the result between this 1D element, because it's T-section with the same effective width of the flange, I should get somehow very close results. So here I have 18 point something, 18 point something. In the case of inverted beam, I have 21, 22.9, something like that. And in case I have connected everything in the center, I have also some nice result. And now if I deactivate everything, so there is no rib action, then definitely I should get something different. And now 18, still 18, but here I have 4.7. And this is quite indication that we're taking into account the rib into account. The second model I would like to show you, it's a little bit more complex. I have a kind of a plate supported by ribs everywhere, and then I model the same but with the normal beam. So there is no rib action here. And I will do the same scenario, and I will compare the result. Going to the CDD calculation, activate the rib, and then run the calculation. I already did the calculation in the background. What we can see here, we have 9.1. Here we have 8. So we have some differences, and this difference is quite logic because I'm taking into account the effective width for the calculation of the rib. But now, in order to be sure that the calculation is logic from SCIA Engineer, if I deactivate the rib action, then the two cases should be quite similar. And as you can see, 8, 8, 8, 2.5, 2.5, 1.8, 1.7. So the result is quite close to each other. And as a conclusion, I think now we have a better solution for the calculation of the CDD. You can model your beam as a beam, or you can model it as a rib. There is no issue. In both cases, you will be able to do the calculation. So I'm going back to the main presentation. The second topic I would like to explain, it's about the calculation of the compression zone. If you are familiar with the NEN National Annex and you read chapter 6.1, in fact, you will know what I mean by the compression zone, because according to the NEN National Annex, you have some you need to limit the compression zone. I mean the ratio between the compression zone to the effective depth of the cross section with this value. And based on the value of FCK, we have two formulas to make the limits. Already that implemented in SCIA Engineer since the beginning of the new concrete, so there is nothing new. But what we made recently, in fact, in some cases, when you do the calculation of the compression zone limit, in some cases you will get a new unity check bigger than 1 because the limit, it's not fulfilled. And then we received some complaints from the clients asking, okay, I know you are trying to follow the NEN National Annex, but in some cases we don't want to do the checks. I don't want, as a user, I don't want to do the checks. And the second issue that I would like to mention, in the past, before 18.1, in fact, we're doing the checks of the, or let me say it in that way, we are calculating the compression zone based on the internal forces. So you have MED, and based on MED, we do the calculation of the compression zone. So in 18.1, in fact, we implemented a new approach, and you will find this new approach inside the concrete setting. So as a user, you have, in fact, 3 different possibilities. If you don't like to do the check of the compression zone, then you can select no verification, and in that case, SCIA will skip everything for you regarding the compression calculation, or you can do the calculation of XU based on the action load, which is as it is before, and the new one, it's based on the MRD, based on the resistance. So this option, in fact, giving you more conservative result, and this one should give you more realistic result. So it's up to you to decide which method you would like to follow. And by default, this one will be the valid one when you start a new project. So let's see, what does that mean? This is the case where you have no verification. You will get the result just like that with the compression value here. And then based on the internal forces, SCIA will do the calculation for you and check the compression zone limit. And the third one, based on the resistance. Let's make it more practical. I have a project to show you. And this project, in my point of view, a very common case. You have a steel structure, and this steel structure somehow supported by a beam, and the beam directly placed on the soil. I guess this is quite a common case where you do the model something like that. So now if you go to the concrete menu and you go to the capacity design and run the calculation to be sure that your capacity is okay, as you can see, let me select only this member, make it like that. So as you can see, now the capacity check everywhere, it's okay, but I have a value 1.0. In fact, in the background, it's not 1.0, it's 1 point something, so it's bigger than 1. And now if we go to the detailed output to see what is happening in this section, so here's the information about the section, and then we will reach this level where we have the explanation of the compression zone. So SCIA telling you, we are calculating the compression zone based on the internal forces. This is the old scenario from SCIA. So I'm talking now in any version before 18.1. You will get the result based on the internal forces. And as you can see, the differences between the compression limit and the compression zone, it's quite minor. It's just 1 millimeter. But unfortunately, the result, it will be not okay. And definitely, I'm not going to put that in my output. So the clients was asking us, is there any workaround to deactivate that? We told them, yes, go here and change the national annex, use anything, not the NEN. And it was very expensive workaround for the clients because they will lose their result. But with the new solution from SCIA Engineer, I'm going to show you the setting. Here you will find this option, calculation of the limit of the compression zone. By default, it should be on the resistance. So if I will do the checks again on the resistance, on the MRD, SCIA will check the MRD everywhere, and then you will get the unity check more realistic compared with MED. And now if we compare the result, you see that the value of X little bit different. The value of the limit also, it's different. And someone will say, why it's different? Why it's different? Because the D, as you can see, it's different. It's a case where we have a biaxial bending moment, and then the D can be different from one equilibrium to another one. But as a conclusion now, we have the same compression, which is used here in the check, but as a verification of the compression zone, we have another option. And now let's go back again, select the third one, no verification, click OK, and then I will do the check again. What we will see a message from SCIA Engineer, and this message telling you, okay, we ignore the verification of the compression zone based on your decision. In my point of view, this is quite clear, I think, at this moment now for you. So I don't want to take more minutes for that. The third topic from my list is the design of beams, columns, ribs, but according to the SCIA code. In 18, we released the new design according to the SCIA code, but without the reinforcement design. So the user was capable to do some practical reinforcement everywhere and do the checks. Now, starting from 18.1, the user can calculate the required reinforcement, the provided reinforcement, and he will see the nice output, the detailed output in a similar way as we have it in the Eurocode. With the figures, everything should be similar. Also, the solution supported by checks with AS maximum, with AS minimum, all the requirement from the detailing provision, all that now it's supported for the SCIA code. I give the words now to my colleague, Iveta, and she will explain to us the new improvement regarding the composite and the steel code check. So please, Iveta.
Hello, can you hear me? Okay, that's good. So I will present now improvements related to composite design. So what we had in version 18 is optimization of composite floors, taking into account possible solutions based on number of studs, cross-section, adding camber to the beams. And in version 18.1, we have a continuation of this. So what we did is we extended the scope of our solution, looking into 3 NCCIs, which let us, for example, design beams with multiple web openings. So to summarize what I will be showing today, first of all, what we have in 18.1 is the possibility to design beams with web openings, so a number of web openings on a single beam in SCIA Engineer. For this, we are following the Steel Construction Institute publication P355. The next thing we did is we looked into minimum composite action. So this is related to the number of studs that you have to place into the beam in order to achieve composite action between the floor and the steel beam. So for this, we implemented the findings published in the Steel Construction Institute publication P405. And the last improvement we have for composite, this is the check for natural frequency. And what we did is we improved the solution that we had for the, let's say, simplified traditional estimation, which is also mentioned in the SCI publication P354. So first I will start with the web openings. Just to give you for the ones that didn't follow the what's new in version 18, it was possible to design a composite beam with a single web opening in version 18. So just a few words on the construction practice for the ones of you who haven't designed composite floors yet. In reality, in construction practice, it is very common that composite beams have web openings, and the reason is that various installations need to be placed in the floor. You can imagine that in the case of this particular composite system where you have the steel sheeting and the steel beam underneath, if you have to put all the installations on the bottom, you will get a huge height of the floor, which would in general increase your costs for building the building significantly. So putting the installation within the floor is quite a practical solution, and also it limits costs, and it's easier to execute, and etc. What is also common in design is because the ducts have certain size, they often determine the size of the beam itself. So what do we have now in SCIA Engineer version 18.1? What we did is we integrated the definition of openings fully in the beam definition. So you can see them on the 3D scene, which was not possible in version 18. And also they are taken into account in the FEM model. Then the next thing we do is we have the strength and serviceability verification. So for strength, we go for publication SCI P355. And for serviceability, we take into account the additional flexibility based on the finite element results. Then what we also have is auto design in the case of multiple openings. So the auto design is, let's say, limited to changing the section of the beam, changing the number of studs, and adding camber. Of course, we do not move the openings that you have defined. In certain cases, it may be more economical to for example, change the size or the location of the openings. And what we do in addition also is we check all the necessary detailing checks and the so-called practical geometric limits. These are limits, for example, on one hand, if you have a stiffened opening, is it possible to weld the stiffeners on the beam? But also these practical limitations are linked to the transfer of forces between openings and, for example, the opening and the part without the opening. So a few words about the publication that I mentioned. So the title is Design of Composite Beams with Large Web Openings in accordance with the Eurocode and UK national annexes. It's a publication from 2011 from the Steel Construction Institute in collaboration also with Tata Steel. So what it offers us is strength verifications for circular. So we have circular openings, rectangular openings, but also elongated openings. These are usually obtained if you have two circles and you cut the web post to obtain a large opening. Also the combination of these, so if you can see here a rectangular opening next to a circle, next to an elongated opening, this is also supported. Also the eccentricity of the openings can be different for neighboring openings. So the method which is published here is a general method which is based on the Eurocodes, Eurocode 3, 4, and 2. And also it is applicable to openings that are alone on the beam or widely spaced, which would mean that they don't influence each other. Imagine if this opening was further in along the beam. And also to openings that are closely spaced, which means that the behavior of one opening is affecting the behavior in another opening. So the method has been verified by finite element analysis, and also there has been a serious campaign to test full-scale beams and verify the method explained in the publication. I will summarize it here and then I will show some things in SCIA Engineer. I will not delve into the details of the publication. This we can handle on the level of another webinar, or you can send me questions if you're interested via support or directly for the ones who have my email address. So now what do we do in SCIA Engineer? We verify at the openings whether the reduced section can take the internal forces that are acting on the composite beam. We are also checking whether the web posts, so the web posts are the things in between the openings, so here, or also the large web posts, but these are sometimes less relevant. So we also have checks on web posts, and we also have the SLS checks. And here I've provided a table to more or less summarize what we do. So the checks at openings, we are checking that bending, so the bending moment can be transferred around that opening. The shear force can be transferred with a reduced section. And we also have Vierendeel bending and also shear buckling, taking into account the presence of the openings. Then at web posts, we are checking a shear, which is coming here, a horizontal shear. We also have the bending of the web post and the buckling of the web post. And we also have quite a sophisticated method to evaluate the shear in the case that openings are close together. So if you have close openings that are close to each other, you will have more sophisticated behavior because the shear has to get through this reduced cross-section here of the web post. In addition, we have the serviceability limit state, and this we take into account by increasing, or on the level of the finite element analysis, the total load deflection is increased, as well as the live load deflection, and also the stiffnesses that determine the natural frequencies will also be changed. So I will show directly in SCIA Engineer. Before that, I will just mention that if you fill in the survey for this webinar, there is a question there whether you're interested in a webinar specifically related to composite design and what is new in version 18.1. I have quite many things to show you there related to web openings in particular that I will not have time to show today. So if you're interested, please fill in the survey or indicate here in the chat that you're interested in such a webinar and we can plan it. So I go to SCIA Engineer. So here I have a very simple structure, which is a composite deck. So this composite deck here, you will see a 2D plate, standard 2D plate, composite deck, rigid diaphragm. It distributes the load via the tributary area method. So here you can see the tributary areas per beam. Nothing new related coming from, if we compare with version 18.1, and what is new now is that I can define, let's say, the openings on the beam, and I can use them in the checks. So if you go now to the structure service, here under 1D members, you have 1D member components, and there is the opening item. So it's the standard opening that you use regardless if it's a concrete beam, a steel beam. It's a general SCIA Engineer functionality. So here, when you open this dialog, you will see rectangular, circular openings, and the cross-section, these three, rectangular, circular, and cross-section, were available in the past. We also added the elongated type specifically for composites to, let's say, from usability point of view, that it's easy to define. So here you can say, okay, 450, and here you say like maybe 250, and then you choose your beam. And here is the opening. Keep in mind, if you are testing this functionality and you're not yet familiar with the opening functionality in SCIA Engineer, that there is a tick box here, which is use the opening for analysis and design. At the moment, it is switched off, so it's possible that you can see the opening and it is not taken into account in the analysis and design. This is in the case if you have a very large model and you would like to temporarily ignore the effect of the opening, you can switch them off. So I will keep this one switched off because I've calculated my model. And another thing I forgot to mention is that you can also add stiffeners on the opening. So here you can say, I would like to add double-sided stiffener around this opening. You can select the steel grade. So it can be this one, and the geometry of the stiffener. And also for changing the location of the opening, you have here geometry. You can say I want it at 6 meters, or you can use relative coordinates to define it. Now, let's use these defined openings and go to the composite service. And there, practically nothing new. Let's just select, let's first select the opening and select a few beams and go to the composite checks. So let's run the checks for a result class. So this result class is the automatically generated one. It creates, it has the combinations for ULS, SLS for the construction stage and final stage together. So here, let's run the checks. So and now we will get the unity checks for these beams. What I have to say is that also if you have many openings on the beam, the checks in 18.1 are slower, which is unfortunate, but we are working to solve this in the following version of SCIA Engineer. So here the checks will run, and I obtain that now I have extreme shear inside my beams. At least for these beams, so the cross-section is not sufficient. So I will run auto design to remedy this problem. I guess that the openings are relatively large if we look at if we compare them to the size of the beam. I will activate result locking so I don't lose my results, and I will start the auto design. So the auto design suggests that I should switch this beam to a larger beam. So this is a 300 millimeter, 305 millimeter beam, switching it to a UB 406. So I change the cross section, and now I have, let's say, the increased cross section, so I can refresh the results. You can see also that the cross section, the openings are defined from the middle of the beam. So in this case, the eccentricity that I defined is again used, but I didn't have to move the opening. So the relevant point here for the definition of the opening is the, let's say, center of gravity of the section. So here I have again my unity checks. Something is failing. Let's go and check what is happening with my beams. If I would like to check them individually, I can go here and say extreme per member, and then I have the various unity checks listed in the table. So I go and I select this beam, and it's on my other screen that it appeared. So just I have to refresh the report. There it is. So if we look here, in the report, what is new, we have this opening for design. So we have here, it says that there is a circle, a rectangle. Here you can see it better, circle, rectangle, and an elongated opening with the geometry, whether there's reinforcement, what is the eccentricity. Then we have the 3 web posts. So here you can see this long one is the one in the middle here. And then we have these so-called practical geometric limits, which are coming from the SCI publication, also for the web post. So these checks are done and you get a report that they are all okay. And then we go and we check the various ULS checks. So here this is nothing new. So these are the checks for the construction stage. And then we have checking the openings in the construction stage. We see bending moment is utilized at maximum. And then we also have the standard unity checks for the final stage without openings, and the unity checks of the let's say of the openings. I've selected the option here. You can see it. It's like openings and web posts to see the extremes or all. So if you want to see all of the openings, you can get a table per opening, and this is showing just the extreme opening. So these are the failure modes for the openings, the 4 failure modes, and here we have the web posts, the failure modes for the openings. So here we have actually the 4th failure mode is not performed because these are not closely spaced openings. So here on the level of SLS, these are failing, but I should recalculate my model so to get the actual unity checks now taking into account the larger cross section. So after recalculation, these unity checks should also be below 1. And then I have all the detailing checks, and I also have the stud layout. So this was the web openings. I will switch back to my presentation and I will tell you a little bit about partial shear connection. So what is partial shear connection? This is a very common way to achieve economic design when it comes to composite floors. It means that if you don't need to transfer the full force, so transferring the full capacity of the steel beam to the concrete or the full capacity of the concrete to the steel, but you only want to achieve certain moment capacity that is enough to take the loads on the structure, you don't have to provide full connection. You don't have to put many studs along the beam. You can use partial shear connection, which is usually more economical. Eurocode 4 gives minimum values for the minimum shear connection, the minimum composite action that you have to have on a composite beam. And we also have the publication from the Steel Construction Institute, which is looking into that into this topic in more detail. So it's also based on recent research, and it also gives various scenarios for the failure. So to put this a little bit in perspective, I want to plot here the minimum shear connection coming from the Eurocode. So in the Eurocode, we have 2 different rules that we can use for minimum shear connection. And you can see we have the 40% shear connection, that is the overall minimum. And as the beam span increases, the minimum shear connection increases as well. So if you have a 15-meter long beam, you will have to use, for example, more than 60% minimum composite action. Now the alternative case is with a very limited scope of application, so most of the time we have to use this curve. So both of these curves are implemented in SCIA Engineer and have been implemented in SCIA Engineer for a few versions already. To give you an idea about the SCI, so SCI publication P405, according to the Steel Construction Institute, the design of composite beams is often controlled by this requirement to have a minimum degree of shear connection. This is also coming from the fact that the beam utilization, let's say the bending utilization, is assumed to be 100% in the Eurocode context. And so in reality, the bending utilization of the beam is not always at 100% due to, for example, SLS limitations. And the fact that we have one rule for all cases, so this is, let's say, one formula that is depending on the beam span and the steel grade, it makes it also more conservative in many cases. And as a result of using this minimum shear connection, we even have lower utilization at the end when we take into account the extra studs that we are adding on the beam. This means more labor costs because these studs need to be welded on the beams. And as a result, we have some additional research and some additional proposals on how minimum composite action should be handled. And here I've plotted a few of the curves. So this publication gives, let's say, various rules, various curves that you should use in different cases. So, for example, if you have a beam perpendicular to the sheeting, a beam parallel to the sheeting, a propped beam, a not propped beam, in different cases, you have different formulas for the minimum composite action. But as you can see, these curves generally lie below the Eurocode. And where we have an overlap with the Eurocode, that is if we have full utilization of the beam, which means that the bending moment acting on the beam is the same as the capacity of the composite cross-section. I've plotted these curves for 70% utilization, which is very often happening in practice. And then you can make a comparison between the values of the publication and the Eurocode. Also here, I show you 90% utilization and 50% utilization for bending. And you can see the differences in those cases. So to summarize the findings of this, the implementation of this publication, we have the findings of more recent research, taking into account modern sheeting geometries, where in general we have less concrete in the composite slab, and also the so-called ETA minimum. This is the minimum composite action, is now calculated not just based on the steel grade and the span, but also the bending utilization, the slip capacity of the studs, also depending on the size of the let's say the magnitude of the live load, sheeting shape and orientation, etc. This publication is used together with some additional detailing rules. And when you use the composite module in SCIA Engineer, keep in mind that sometimes these detailing conditions may actually give you more studs. So keep in mind that this is a possibility. And then if you find that your design is not economical, just switch to the general Eurocode case. So it's possible to use the publication, let's say, or not, use it or not on the level of the beam. So in SCIA Engineer, the user can influence the choice of curve, so the rule that is used to determine ETA minimum, but only within the limitation given by the publication. So if the publication says that this formula cannot be used in the case that you have, then it will not be possible to do that. Also, by using less studs, we will have beams that are more stiff, less stiff. So your composite action will affect your deflection. And this is also taken into account in SCIA Engineer on the level of the FEM analysis. I give you here, let's say, a proof of concept. I have here a 12-meter beam, which I have designed using the SCI P405. So the publication lets me use 30% composite action, which results in 7 studs in each of these 2-meter long regions or segments. So if I had used the Eurocode, I would have to put 12 studs in each of these let's say regions, and instead of 30 centimeters spacing, I would have to either switch to 2 rows of studs or use 16 millimeter spacing. And then the last extension that we have for composite is a better calculation of the natural frequency. So this was version 18 for the ones who followed the version 18 webinar on composites. I said at the time that our vibration check is often conservative, and we noticed that in many cases it was more than 1, so it was failing. And now in version 18.1, if you run for the same model, you will find that the vibration check is passing. So what did we do? We didn't cheat in this case. What we do now is that we take into account that when we are evaluating frequency or vibrations, we always should assume full composite action. This is because regardless of the number of studs on the beam, with such small deformation that are caused by vibrations, the slab and the beams always behave as one. And another thing we are using now is also the dynamic modulus of elasticity. So when you have dynamic loading, the concrete is also behaving more stiffly. So by using these two, let's say, corrections on the stiffness of the model, we are able to get different values of the natural frequency. Also, we added some additional options. So it's possible to change the frequency limit. Instead of 4 Hertz, you can put something else. Also, you can change the percent of live load which is considered when you're evaluating deflection. This was a request coming from France, where apparently in a local publication it was possible to use 20% of the live load for the calculation of the natural frequency. So this you can change in the composite setup. And also you can switch the vibration check altogether if you are not interested in it. Here is the output of the vibration check. Here you will find all of the recalculated deflections, taking into account full composite action and dynamic modulus of elasticity. So the wrap up for version 18 for composite. So we have a robust handling of multiple web openings on the beam. On the level of analysis, here you can see how the deflections are changing when you have openings along the beam, and also on the level of the checks. We have less stringent limitations on the composite action based on the Steel Construction Institute publication, and we have an accurate calculation of the natural frequency. And the benefit is that you can design more economically, first by allowing the installations to pass through the floor, and second by using fewer studs to provide minimum composite action. And also you have a clear indication of floor vibration issues. The next thing I will mention, it's a big improvement, but I only have one slide about it. It is the new, let's say, possibility in the detailed output of steel code check is now we have formulas. So I am not going to spend more time in PowerPoint. I will directly go to SCIA Engineer. So we go to Steel Service. And there, when you run ULS checks, let's grab one beam, and yeah, let's select here some combination, and we want to get the detailed output. So here you have possibilities. You can say, I want to see formulas, or I want to see the tables and the formulas. So let's say we select this option, and so we refresh for this column, and we get the output of the steel code check. So what you will see, so this is the classification. It was quite, let's say, long to put inside anything else but the table. So the rest of the checks, so you have all the checks are listed in with formulas. So interesting is the bending and compression check according to the annex of Eurocode 3. Part 1.1, you know that this is a quite sophisticated calculation, and so now today it is possible to check all of these calculations with formulas. I think there's nothing more to say about this. Enjoy using it for the ones who are using the steel code check. And I'm at the end of my part of the presentation, and so I would pass the word to my colleague Jaroslav.
Hello, also from my side. I'm Jaroslav Bros, and I will lead you through the rest of the presentation during our webinar. And I will start with topics related to increased efficiency and streamlined usability. The first topic already mentioned during the content of this webinar at the beginning was mentioned. That's a bill of material. You as a users missed this option under the new post-processing environment. We take this as a feedback from you and develop it also in this environment. You have already access to information related to the mass, volume, and surface for all used materials like concrete, steel, aluminum, etc. There are also 3 types of sorting, which I will show during the live presentation. And what's at the last is possibility to raw price estimation of the analytical model. I will switch to the SCIA Engineer. I hope you can see my SCIA Engineer with the model of the steel hull. What's the basic and the default type of the sorting? That's the sorting according to the used materials. As I have steel hull, I have just steel, nothing more. What I would like to share here with you, that's also a possibility to do the type of sorting member, which is just related to 1D members and perfectly suits this example. Once we have here the table with the results, you can see that here I have listed all cross sections which I used in my model, together with the material and also together with their count in the project. It means how many of these members with length of 3 meters with cross-section U100 is used in the project, together with unit mass, surface, volume. So that's what I can do for 1D members. If I will switch to the project where I have mixed concrete structure and steel structure, I can show you also the bill of the material for such a model after a while. So let's me go to the service results with bill of the material. And here I would like to present you a type of sorting which is related to the cross-section. Just click on the refresh and you will see what we will see in the tables. We have sorted tables according to the material and according to the members. So 1D, 2D. In the case of the 2D, the sorting is done according to the thickness of the slab. In the case of the 1D, sorting is done according to the cross section. So that's a pretty handy tool. What I didn't mention yet, that's the possibility of the price estimation. So I would like to do the price estimation for concrete and steel. I have here the default values related to the project, so I can choose 15 and 20 as an example. And later on, we will see that the table will change accordingly, that I will have the total summary according to the materials, and then summary for every table. Let's wait on the regeneration. Yes, is here. So you can see the price for each row plus the total sum. That's what I wanted to show you, and it's related to the bill of the material. When I will go back to the presentation, And switch slide. Then the next topic, which is released and it's attached to the analysis and results, that's the relative deformation in post-processing environment V17. And you can check these intermediate results for serviceability limit checks, mainly for mainly for steel structures. The benefit is that that's a faster processing compared to the old one, and also that you can use the wider possibility of the presentation of the results, and you can have also the results informations on the picture related to the relative deformations. The next topic, it's related to the extension of calculation reports. As you may know when you have an experience with the usage of SCIA Engineer, you know all the messages at the end of the analysis. So we have been thinking about it, and we wanted to provide some useful information after the analysis. Here you can see the results of model analysis. That it's okay, as you are used to from the old dialog. Here I have information related to the number of calculated eigenmodes, and what's also included, that's the sum of relative model masses, so you can easily check during your seismic calculation if you fulfill the rule from Eurocode that you have to have at least 90 or 95% of the masses participating in the analysis. Then for the linear stability, we have information related to the number of critical factors, plus information about the first critical factor for each stability calculation. So you can easily see what's the critical load factor for your structure and stability combination. And then the rest is related to the results for nonlinear analysis. What we also did, and that's the extension and, let's say, the modification of the dialog for the running of the calculation. Here we offering the possibility to regenerate the defined engineering reports. So if I have 3 engineering reports, I can select which ones I would like to regenerate after the analysis. And on the last here, that's the possibility to save project after the analysis. So I can in advance create engineering reports. I can do all the stuff. I can just check these 2 tick boxes, hit the calculate button, and go something better than designing of the structures. That was what was also related to engineering report, and that's the next topic. That's the possibility to direct export of engineering report to Microsoft Excel. In the past, you have been used to use the export to MS Excel via HTML file. We improve it, and we are now natively exporting the XLS format. So here you can see the definition in the engineering report. Here is the result. So it's easy to read, navigate in the output. The last thing, what I would like to show you and to share with you, that's the extended information flow in BIM. And that's mainly related to the possibility of import IFC4 file. So if you are using CAD softwares like Alplan, Archicad, or some other CADs, now you have the possibility to export IFC4 file from these softwares and use it directly in SCIA Engineer as you are used to. Just go to the file import and select the IFC file. SCIA Engineer automatically recognize if it's IFC 2x3 or 4 and display the dialog which you are used to see. What's have been also extended, that's the support of the definition via the tessellation geometry. That's what's included into the definition of IFC4. In that case, you will get this result, and then you can use the BIM toolbox to recognize the standard element types like beams and slabs. So that's, I think, the unique feature for you, that you are now able to use also IFC4 with SCIA Engineer. And that leads me to the end of our webinar with a short summary. We have been talking about multi-material design and floor systems. You have seen the development related to the long-term deflections, extension of code for Switzerland, economical design according to Eurocode 4, transparent output with formulas in steel check. You have seen the application of bill of the material. You have seen the results of relative deformations, extended calculation reports after the analysis with rich information related to the calculation, direct export of engineering report into the MS Excel, that it's native format XLS, plus for BIM, that's import of IFC4. We are at the end of our webinar. So if you have some short questions, you can type it and we will respond it into the question box. Thank you that you attended our webinar, and have a nice day. I don't see any remaining questions in the box for questions. If you will have some further questions, don't hesitate to contact our support and we will reply on it. So once again, thank you that you join us today and have a nice day. Bye-bye.